All right, well, get ready for something really cringy. So, to make it more interesting, I thought I would be a little more involved in my lecture. And so, here we are. I am in my lecture, right? And just to make it even better, I thought I would dress up. So I wore my Pac-Man suit. I usually only reserve this for special occasions, but prom probably isn't gonna happen, so here's my suit, my Pac-Man suit, right? Maybe later we'll have some sort of option where you can help pick what outfit I'm wearing for the next lecture, but we'll get to it later. Anyway, this is the last section, the last learning target of our notes for this unit, and let me think here. I need to be, which way? This way, I think, off to the side, so you can kind of see the title. I can't actually see it, it's just a green screen here, but there at the bottom is the title of our learning target. This is the, like I said, the third learning target, so this is C, which is star death. Okay, we're going to talk about how different stars die and how it works out. So here's the other side of that learning target. So here we go. This is going to be really bad, and I don't really know what I'm doing, but we'll give it a shot. Okay, so at this point in the story of our star, we're going to say that the star was born and it's going through its normal life, right? It's fusing hydrogen into helium. It's balancing the forces of gravity, and everything is going well, okay? That's our normal start there. Hydrogen is the fuel. The core is pretty stable. Everything is balanced, hydrogen to helium, into heavier and heavier elements, okay? Now, eventually, that somewhere in here is our sun and its main life, okay? And then somewhere over here is going to be the next step of our sun's life, right? This is going to be the giant stage or the red giant stage, depending on the size of the star. And basically what's happening is, as it's running out of hydrogen to fuse into helium, then it's going to fuse helium into the next heavier element, I believe it's carbon, and then carbon will fuse into something heavier and heavier. And when it does that, it gets bigger, right? It expands. It's going to take more energy, and so that star is going to expand. And if this is the case, right, this is what's happening with our star, then what's going to happen to some of the inner planets? What would happen to Mercury? Gone. What would happen to Venus? Gone. Earth might be right up to the surface of the sun, or itself might be consumed by that star. So main sequence, main life, and then it goes into a giant stage, a red giant stage with it. Okay, here's what we have, kind of a map of the life cycle of a star, and I'm trying to stand out of the way. At the top you can see what's going to happen to the star, the fate of the star, if it's a low mass star, okay? And at the bottom it's going to be the high mass star, and I'll move over here so you can kind of see the end phase of both the low mass and the high mass star, right? But what I want you to notice at the beginning is they both start the same. Right? They both start with that cloud of gas and dust, that nebula. They both then will go into some sort of main sequence average star. Low mass, like the sun, might be yellow. The higher mass might be burning at a higher temperature, a bluer color, right? And then after that, when it starts running out of hydrogen to fuse, then we get into those giant stages, and it's somewhere in the middle, right? Red giant stage or a super giant stage for the high mass star. And then we really start to divide into two different paths. So for now, we're going to follow the low mass stars up top, and then we'll come back to this, and we'll follow the low mass stars below. Okay, continuing our story with our low mass star. We had our normal main sequence life. Then we had a giant stage as it was starting to fuse different elements, heavier and heavier elements. Eventually, it's going to kind of run out of anything to fuse. And then we're going to get what you see here. Okay? This is also a type of nebula, but this is called a planetary nebula. And basically, the outer gases are going to get stripped away this planetary nebula, and what's left behind is somewhere in the center here. If you look closely, there should be a white dot somewhere in the center. That's called a white dwarf. A white dwarf is basically like this. Imagine that you turned on your stove top and it got red hot, okay? And then you turned it off. Would it still be hot? It would, right? Would you want to touch it? Probably not. It still might even be glowing some. That's what we have here with the white dwarf. It still might be glowing and showing some of that energy, although no more energy is being produced, no more fusion is occurring. So it's basically like a light bulb that's slowly dimming over time. Eventually, this white dwarf is going to run out of that leftover energy, and it's just going to be a black dwarf, or I think sometimes they refer to it as a brown dwarf, right? You could also think of this if we go back to our gambler analogy. This is a star that's just running out of chips, right? This would be like a retired star, and it's just using its savings to extend its life a little bit longer. But ultimately, that thing will be gone. It'll just be a mass of atoms, just kind of cold in space. Okay, so now let's take a look at what happens to our high mass stars. Again, we're going to start the very same way, just at a hotter temperature because it's more massive. So you can see when you compare those two, you have a blue star there, it's just burning hotter. When you get to the red giant stage or supergiant stage, it again might be hotter, might be bigger because it's more massive. What really is going to separate the low mass from the high mass is going to be the ending part over here, okay? And so we'll talk about this briefly, but on the ending phase, depending on the situation, we could go, we're going to have, similar to that planetary nebula, we'll have like a supernova explosion, okay? Very similar to the low mass star in the situation. But then the result is not going to be your white dwarf. For a high mass star, we'll probably have a neutron star, and we'll talk about what that is in a little bit. And then for the really, really high mass stars, it's possible that we get down into our black hole. That's only for the very massive stars. Okay? So let's talk about one of the two options when it comes to a high mass star at the very end. Okay? At the very end, after its supernova and its explosion, it's going to have a collapse down in on itself. Okay? And when it does that, something unusual is going to happen. It's going to have so much weight and so much pressure and so much force that the electrons and the protons are actually going to be pushed into each other and collided into each other. Now, if you take a positive thing and a negative thing, you put them together, you have something that's neutral. Well, if that happens with all the atoms of this star, they're all neutral, then we have this thing here. That's a neutron star, right? Neutral, neutron. That's what we have here, okay? This is only going to be high mass stars 10 to 100 times more massive than the sun. So this is not the fate of our sun, this neutron star. But think about it like this. If we took our sun and you multiplied it by 10, or you multiplied it by 100, that'd be a pretty big star. If we could squish that down to the size of this, that's a lot of stuff in a small area. Okay, now I don't remember what actually is in the background, but I think it's part of New York, right? The state of New York, with some of the river and cities with it. So imagine the sun 10 or 100 times larger than it is, and we squeeze it down to the size of New York City. That's a lot of stuff in a small area. Very, very densely packed in material. Okay, finally, here's what probably we've been waiting for, is a black hole. Okay, and a black hole is something that still has a lot of mysteries with it. If we have a high mass star that is massive enough, this is one of the possibilities that could happen. Okay, very massive stars that have gravity so great, the mass is so large, the gravity is so large that even light can't escape it, is what we call a black hole. Okay, and obviously this is not a real black hole because, well, it's not, right? Just recently, I don't know if you saw this or not, but just recently they were able to actually photograph a real black hole, and maybe I'll try and find it, and if so, hey, there it is, right there. There's the actual black hole. Okay, now, besides this photograph, how did we know it was there? And when I say we, I mean smarter people than myself. Well, if we have planets or objects in space that seem to be going around something, but we can't see that something, then we might start to think that a black hole could be there. It's a very simplified explanation of it, but that at least get us maybe in the right direction. Okay, lots of different theories about what a black hole is, what it could be. Could be something where, if you can see this, where it's like a wormhole or a warp into space, right? Where you go down one side and go out the other into a different part of the galaxy or the universe. Who knows? Lots of possibilities, okay? Current scientific belief suggests that if you go into a black hole, you will be stretched out into an actual process they call spaghettification, where we take every atom and line it up and kind of spaghettify you out. So that probably won't be ideal for you. Okay, but that is the fate of a very, very massive star. So much mass, so much gravity, even light can't escape it. Star track, our high mass star track, again, they start very similar, very main sequence, hydrogen to helium. As that starts to run out, that's like the beginning of the end, and we'll have the swelling stages, the giant stages, and then some sort of explosion, either a planetary nebula or a supernova. And then for the low mass star, you're going to have your white dwarf and eventually maybe your black or brown dwarf. For your high mass star, you're going to have a neutron star, and then at the very end, for the very massive stars, possibly a black hole. One last thing to show you here, and if you look on this side, here are 4 different stars. We've got the sun, we've got a white dwarf, we've got a neutron star, and we've got the Earth, just for comparison. Okay, and we have a couple different columns here. The first column is the volume, and we have the mass, and then we have the density, and then finally we have the mass of those 4 things, the mass of those 4 things, if we had just a teaspoon of it. Okay, so for example, if we had a teaspoon of the sun, it would weigh just over 7 grams. 1 teaspoon of sun is about 7 grams. Right, that makes sense, relatively light. Let's skip down to the Earth. 1 teaspoon of Earth is going to be about just under 30 grams. Okay, density-wise. If we grab something like a white dwarf, okay, it's going to be about 10 to the 10 times 10 to the 6th power, right? Grams. So that's actually pretty massive. 1 teaspoon. If we had a teaspoon, and we can see even further here with the neutron star, that's 3.28 times 10 to the 15th power, right? Which is a whole bunch of zeros and a lot of numbers. Let me say it this way. If we had a teaspoon of neutron star, and I just spilled it out, right? It would cut its way right to the core of the Earth, just like a brick through water, right? That's how densely packed in these things are. Now that's a neutron star. What about a black hole? I would guess it's even further, even more. So some interesting numbers to consider when we're talking about density of these objects. Well, that's it. Like I said, this was super awkward. If it's awkward for you, imagine how it is for me. And yeah, there we go. I thought this might be a little more entertaining, and maybe it is. So maybe we'll try this again, some more lectures next week. Otherwise, talk to you later.